So we built all of this mechanism up so that we can write reliable, composable smart contracts. Here's where we get to the payoff. This last section is kind of the punchline of the whole talk. So how do we use all of this infrastructure to write smart contracts that are more reliable, more understandable, and especially more composable? So the smart contract layer, this layer of electronic rights and smart contracts, is really a distinct level of abstraction than the object layer. In order to understand this distinction of layers, we need to see how to build an electronic right out of objects. And the best example for showing that is money. The code on the right implements money out of objects, and it does so following the pattern you already saw in the counterexample. On the outside, there's a make_mint function. And every time the make_mint function is called, it creates this triple of a new ledger, a new issuer, and a new mint. And that triple represents a distinct currency. So every time we call make_mint, we get a new distinct currency, and each of these currencies are isolated from each other. Where do new units of currency come from? The mint has a method called makePurse that creates a purse object and registers the purse object in the ledger associated with its initial balance. Now, this ledger is not the normal blockchain ledger. This is an object table. This is a table indexed by object identities. There's no public keys here. At this level of abstraction, we don't see any cryptography. We just see symbolic object computation. So let's call the makePurse method once to create an initial purse associated with $100 in the ledger, and we'll give that purse to Alice. And let's create another one that we give to Bob. Now, how can Alice buy a concert ticket from Bob for $10? The first thing she does is she sends a withdraw message to her main purse saying how much she wants to withdraw. And the withdraw method, what it does is it creates a new payment purse, and then it updates the ledger to move $10 from Alice's main purse into the payment purse. And returns the payment purse to Alice, which Alice then sends as an argument in a buy message, saying to Bob, I want to buy a concert ticket for $10. And Bob receives this payment object. Now, Bob wasn't interested in getting a payment object. Bob wanted to get paid. And there's a big gulf between what it means to get an object and what it means to get paid. So let's go through all the ways in which those are different. When Bob receives the payment object, the red line here says that Alice might still have access to it, and Bob has no way to tell. Whereas Bob's not paid until Alice doesn't have access to that money. The point of an object is mostly to invoke it, to cause behavior, to do something with it. Whereas money is purely symbolic. You can't do anything with it other than trade it further. Objects are opaque. What is it that Bob received when he received this object? He has no idea. It's just some object that he got from someone who could send him a message. Whereas he's not paid until he knows how many units he's gotten of what currency. And objects are specific. Alice sent him a particular object, this specific payment object. Whereas money doesn't need that specificity. Bob is only interested in a quantity of whatever the particular currency is. He doesn't care which particular dollar bills he's gotten. So to turn the object that Bob has gotten into getting paid, Bob sends a deposit message to his main purse with the payment purse as an argument. The main purse looks up the payment purse in the ledger, and if the payment purse is in the ledger, and only then, is it actually a legitimate purse of this currency? Even if it's a legitimate purse of some other currency, it won't be found in this ledger. And having found it in this ledger, it can now update the ledger to transfer the $10 back into Bob's main purse. And it's only when the deposit message acknowledges success that Bob knows he's been paid and releases the concert ticket to Alice. So from this contrast, it might seem that objects are about the column on the left and erights are about the column on the right. Well, objects are about the column on the left. However, by erights, we mean the entire taxonomy opened up by this contrast. All of these dimensions of variations and several others we want to describe through the erights interfaces so that we can write generic contracts that can manipulate any right that can be described with those interfaces and that fits in this taxonomy. There's another way in which objects differ from the world of smart contracts, which is the basic transaction in an object system is the message send, which is a one-way transfer of rights. Whereas for smart contract, the core operation is an all-or-nothing exchange of rights, where either both rights have been exchanged or it's as if nothing happened. An example of an exchange-oriented contract is what's called a covered call option. Say that Bob has bought an expensive concert ticket. And now Bob realizes he'll be out of town during the concert. And he mentions this to Alice. And Alice says, if I give you $10, can you hold the concert ticket for me through the weekend so that I can find out whether I can attend, in which case I'll buy the concert ticket from you. So that arrangement is what's known as a covered call option. Alice has the ability, until the weekend is over, to decide to buy the concert ticket, but she has no obligation to do so. And this is the code needed within our framework to express a covered call option. The important lines are these, where the covered call option first obtains from Bob into escrow the concert ticket that he would be offering, and only once those rights are safely in escrow does the contract create the ability for Alice to participate. In some sense, the contract doesn't really exist as a contract until it has confirmed that Bob's rights are in escrow. And Bob's rights are in escrow until the deadline expires. This line arranges that once the deadline expires, Bob can get his concert ticket back, but not until then. So this contract sits between four other parties: the two issuers of the two rights at stake, and Alice and Bob. And the contracting framework creates these two chairs representing Alice's ability to participate in the contract and Bob's ability to participate in the contract. Now, any contract that unfolds over time creates a valuable situation that Alice, by being able to participate in this contract, by having this role in the contract, until the weekend is over, Alice is in a valuable position. And we would like to take these derived values and turn them into derived tradable rights. So the same contract framework that creates this chair around the covered call option creates it as a chair issuer that can act as in the role of issuer to yet other contracts. So in this example, Alice might be negotiating with Fred to sell Fred the covered call option. And the important thing to understand here is that these contracts are generic. The escrow exchange being used by Alice to negotiate with Fred has no idea what a covered call is. It will trade a covered call in the same way that it will trade money or concert tickets or whatever. The erights framework enables the creation of a wide range of derivative instruments, options, futures, etc., as well as auction institutions, English, Dutch, second price, continuous double. All of these things turn out not to be specific to the particular nature of the right and can handle any right that can be described as an eright in this framework. And that enables us to create the rich composition of contracts that enables our world of smart contracts to reflect the richness of commerce in the real world. And these derived rights to participate in the contract also demonstrate that our taxonomy is real. Like money, it's exclusive. Fred doesn't consider himself to have obtained the option until he knows that Alice doesn't have it. Like an object, its point is to exercise. Bob is interested so that he has the ability to exercise the option and actually get the concert ticket. Like money, it needs to be assayable, so that even though the escrow exchange doesn't know what a covered call is, Bob can explain to the escrow exchange, can describe to the escrow exchange what right it is that he wants, so he knows what he's bargaining for, so that if he get it, he can know that what he gotten is what he bargained for. And like an object, it's specific. It's the right to participate in this particular contract. It's not just some quantity of some generic thing. So, how did we do on the challenges we set out to solve? We addressed the hazardousness by creating a computational paradigm for doing secure distributed programming that can be used more reliably and more understandably by introducing object capabilities, by identifying this disciplined subset of JavaScript, Jesse. By the bang here, I mean the asynchronous communication model for sending asynchronous messages, and most of all, the ability to write contracts as patterns of objects, staying purely within the symbolic realm of objects, not having to go back to cryptographic concepts which are notoriously hazardous to get right. We address the unfamiliar languages by enabling our users to write their code in JavaScript itself. We address the non-composability by this duality of erights and contracts. That contracts manipulate erights, and by manipulating them, they create derived rights, where those derived rights are the kinds of rights that these contracts themselves can manipulate. This is higher order composability, allowing us to build deep networks of highly reusable contract components. And most of all, we're very aggressively cross-platform, avoiding any kind of single chain lock-in. We want to work over a great variety of chains, over non-chains, over public systems, over private systems, in order to bring about the kind of large-scale network effect necessary to give rise to the richness of market phenomena. And now we'll take questions on the whole stack.
Hi, thank you for your presentation. Big fan, by the way. Heard you and Robin Hanson and Eric Drexler talk at the conference. I said big fan, by the way. Thank you for your presentation. And so I have a question generally about IBC, the protocol. Just from a high level, why do I want blockchains to interact?
Why do I want blockchains? I missed a word.
Why do I want them to interact?
Why do I want them to interact?
You know, like the upside of messages passed between chains, like what Polkadot's doing. Why?
The premise of every blockchain is that there will be valuable assets on that blockchain. And for the blockchain supporting general purpose computation, the premise is further that there will be contracts running on that blockchain manipulating assets. If each of those is a separate island, if you can't write contracts that interact with other contracts and interact with that are elsewhere and interact with assets that are elsewhere, then you have a world of separate villages rather than anything like a global marketplace.
Blockchains having a single responsibility principle, this allows for complexity of a system for each blockchain to have something, but then they can also interact for the purpose of creating, I guess,
I'm sorry, I'm not hearing every word.
Better financial system like we have now with derivatives and swaps and options that can also for swaps.
Yes.
In place on public market codes, API, I guess we call that. So is this an API for crypto or for, I guess, messages, contracts?
So our focus is creating the level of symbolic object programming that is independent of the location of the objects that it's interacting with. The layering on top of CapTP, on top of IBC, is in order to enable that independence and enable the rich connection between computations that have been located in different places. The reason there are so many chains is there's a lot of different hypotheses people are pursuing about what the right way to build a chain is. And it's not that one of those will be the winner, that one of those has the right hypothesis and the other are wrong. There are many different trade-offs. These chains are addressing different points in the trade-off space that will continue to coexist. And we want a fabric that spans over that coexistence. So the IBC fabric that we found out when we came across IBC from Cosmos, we realized they're thinking about the inter-blockchain world in very much the same way we are. And in our collaboration, we realized that we can merge our protocol plans into what are now the plans for IBC that can serve both of our interests, but it's essentially the same vision.
It's a cloud service blockchain.
It's Internet of blockchains is a phrase that IBC will often use.
Thank you.
Yeah.
It seems maybe inherent in the way you've designed the graphic here, but to what extent have you made the pieces modular? And for instance, if I don't want to use JSON, but I want to use some Rust-y version of things? Like how easily could I build a subset of Rust, say, to interact with the other layers without having to deal with the specific parts that I don't want?
So if you'll recall the swing set diagram in which one of the vats was a WASM vat, that WASM vat could be a WASM vat running Rust compiled to WASM, as long as it can speak the interface to the swing set kernel, it can participate as a full-fledged citizen in that world. We have not actually done that, but we're architecting the system so that we have that ability. Altogether, we're building the systems in a very, very modular fashion because we want to get as much buy-in as possible for the individual components from people that don't buy into the rest of the architecture. So that's why, for example, collaborating with Salesforce on creating the SES mechanism that they're using in the Lightning platform. They're using SES in the absence of the other technologies. Likewise, with various other technology choices we're making, we're trying to create each of the components so that to the maximum extent possible, they can be used without the other components.
Regarding JavaScript specifically, besides how common the language is there anything else about it that lends itself to this kind of thing? Or would you have preferred to do this with another language?
That is a wonderful question, because the answer, I think, takes many language people by surprise. JavaScript, I've been very clear about all the downsides of JavaScript, all the liabilities of the language that we started from. JavaScript also has some incredible assets which are absent from other industrial languages. So in terms of getting adoption, let's consider only the candidates which are languages used commercially, not academic languages. Among such languages, JavaScript, because of an historical accident, has a beautiful separation between the computational ability of the language per se versus the I/O abilities provided by the host. The historical accident is that the JavaScript, the language, was being standardized under ECMA, while the browser API was being standardized under the W3C. And even though JavaScript started as a language only for programming the browser, that organizational split kept browser concepts mostly out of JavaScript, and in particular kept browser I/O concepts completely out of JavaScript. And that's a real miracle when the browser was the only host. We've done a similar exercise securing Java, where Java you would expect to be a much more suitable language for creating an object capability version. We created an object capability version called JOE, but Java mixed I/O and computation willy-nilly through the APIs in the standard library. So by the time we succeeded at making a separation, the libraries were so different that essentially no old Java code ran in JOE. That separation in JavaScript is really beautiful. Another thing is, I mentioned that part of the rule in object capabilities is that an object can only cause effects by using references. That's been the case with JavaScript. The downsides of JavaScript from security point of view had to do with what effects it can cause and what references it can obtain for causing those effects. But all of the references that enable it to affect the outside world are looked up first by looking up a global variable name in the global environment. And therefore, if you can intervene in that lookup, you can virtualize everything. The way you can build a virtual machine out of a machine that has a clean system mode user mode architecture. In a similar way, SES enables you to completely virtualize the host. So JavaScript code can act as an arbitrary host to other JavaScript code.
Kind of expanding on that last question, what makes JavaScript better than WASM for doing this, or why did you choose JavaScript for this?
JavaScript is neither better or worse than WASM. They're at different levels of abstraction. WASM is an instruction set architecture. It's an instruction set architecture that has the security properties of a process with an address space, where it's a flat address space. And we've seen, for example, with the recent exploit on 0x, or actually the vulnerability that 0x discovered before it was exploited, fortunately. But that was a mismatch between the solidity level of abstraction and the EVM level of abstraction. So it was essentially like a buffer overflow, because the EVM, which is the semantics of the enforcement mechanism, is an enforcement mechanism that doesn't know anything about the objects that programmers think in terms of. Likewise, when people run WASM on blockchain, the WASM plugging into the swing set kernel that you've seen is a WASM instance as a whole. WASM is good at enforcing a security boundary there. But as far as the code running in the WASM, you still have all of the problems of programming language design that you have to solve, because the programmer is thinking in terms of separate objects with memory-safe pointers to each other, and you need to live up to that expectation if the security properties of the platform you're delivering meet the expectations that are implicit in the assumptions the programmers make when they write their program. And I think
I just want to add one thing to that. It's important, these levels of abstraction, that JavaScript is a programming language. A lot of people, oh, we can replace Solidity with WASM. That's not an answer. WASM is not a programming language, except to a very few low-level hackers, right? And they're the ones that will be in the best position to compromise it, but it's not a programming language, so it's not a substitute for a real answer there.
Nevertheless, I mean, we're overjoyed that WASM is becoming widespread in the blockchain world. And as I mentioned, we do plan to leverage that. That makes our life in running our platform everywhere much easier.
Could you speak to the libraries that you expect to be built with these smart contracts? Do you expect a strong standard library to be built by you or a small group, and then a lot of other kind of long tail of contracts? Or do you actually expect the standard library to be pretty rich and robust, maybe similar to how Node and NPM kind of built a very rich and robust library of code from the community? Meaning there's a huge variety of contracts to make here, maybe some of them which can be built out of smaller primitives and then make richer and richer layers. But I'm curious about this kind of stuff because those adoption patterns and the actual what's available in that toolkit and how easy it is to add to that toolkit ends up being a very significant reason for adopting or not adopting a language.
Yeah, I'm very glad to get this question because it gives me the opportunity to emphasize something that I hadn't really emphasized, which is at the smart contracting layer, we're building a rich framework. We're trying to create a rich framework for the purpose of supporting smart contracts in very much the same way that people build rich user interface frameworks like React or rich server-side frameworks. We want to populate that framework with highly reusable smart contract components like the escrow exchange that you saw. And in particular, another interesting virtue of JavaScript is the dynamic range of programmers' skill that JavaScript accommodates is really quite large. It's probably a larger, useful dynamic range than is experienced by other industrial languages. So people constructing frameworks put a lot of care into constructing the framework and constructing the composable components. And then with and the key thing there is that the components, by being highly reusable components, can be deeply vetted by experts creating those components. And then other people composing such components, if you're in a paradigm like object capabilities that supports compositional reasoning about correctness, then you can reliably compose highly vetted components simply into correct compositions.
So I know that WASM ABIs there are actually some compatibility issues there, and so WASM compiled from JS versus Rust might not actually be quite as compatible as you'd think. So do the swing set and the swing sets and the general message passing architecture kind of update those problems?
I'm not sure I got the full question. It was a question about the incompatibility between different forms of WASM?
Yes, so the ABI incompatibility.
Oh, ABI compatibility. Yes, so we actually ran into a problem in our first attempt to run our platform as a parachain on top of the parity platform. And that the problem was exactly the ABI, the binary interface between how the C code that implements the XS interpreter compiled through LLVM to WASM versus the Rust code that Polkadot writes that's compiled also through LLVM to WASM, compiles to WASM in such a way that it's not easy to figure out how to link them together. And that turned out to be a show-stopping problem for us at the time. We've talked to Frederick at Polkadot about this problem. He's aware of it. They know we're blocked on it, and they're working on it. And once we've surmounted this problem, then we intend to revisit building on top of a Polkadot as a parachain. Any other questions? Okay. Well, thank you.